Okay, looks like we got everybody here today. Missed a few people the other hours. We hope you're doing well if you're watching. I think I missed Josie. But we begin kind of our investigation into vectors. Today you want to be able to add vectors, subtract vectors, graph, basically find the general components of vectors, so on and so forth. So vectors have great application in trigonometry. They're kind of the fundamental building blocks of physics and engineering. Anybody take an engineering class here? You did? Okay, you have. Okay, so you maybe encountered some engineering principles involving vectors in those classes, but definitely a good introduction. We just spent a couple days on it. It's nothing that's mind-numbing. The complex analysis piece that you guys just looked at, with de Moivre's theorem and nth roots of complex numbers and things like that, that's a lot more challenging than what you're going to see today. Okay. In fact, a lot of what you see today, you already know how to do. A vector has an initial point and it has a terminal point. It starts at the initial point, it ends at the terminal point. So it's kind of like a ray in that it has direction. However, a ray has infinite length, whereas a vector has finite length. It starts and it stops. The initial point here we call point A, and the terminal point we call point B. Vectors do have magnitude, and they also have direction. The magnitude of a vector is the length of the vector. Maybe you have seen the movie Despicable Me, and you recall the point where he says that his name is Vector, and you're like, why do you call yourself Vector? It's like, I'm both magnitude and direction. And so he's making a play right off of the mathematics, which is awesome, but you guys didn't laugh when you saw it the first time. Hopefully now you will. And yep, it went right over your head, right? Okay, so there it is. Now we're going to learn to add vectors and do things of that nature. So let's just look at a basic drawing. So here we have a vector. We'll call it vector v. And what I'm going to do is I'm going to draw negative v. So it would have the same starting point, but the negative would make it go in the opposite direction. And so that would be negative v. What do you think would happen if I draw 2v? Yep, same vector, twice the length. We're going to use our vector analysis in order to find out how Miss Anderson walked through the portal and arrived in the hallway at half the normal time.
Okay, I just thought it was interesting. I see her like 1 minute ago and then she came down the stairs. I had to do a double take.
You make a really good point, and it seems like you think I'm making fun of the situation, and I would never do that. Okay. All right.
She won't. It didn't actually exist.
What about negative 4v? Yeah, something like that.
Yeah.
6 times, did you say? Too far? Okay. Sam said I went too far. Said, how's that? Is that better? Okay. Half is more than 3/4. Okay. All right. Okay. All right. All right. So now we're going to actually do some vector addition and subtraction. We have vector A, we have vector B. I'm going to draw negative A and negative B. Negative A would look like this. And negative B would look like that. That's definitely. Okay, so now as I draw A plus B, what I do is I need to accomplish vector A, and then I need to accomplish vector B. So for example, as I draw vector B right here, right over the other one, what I'm going to do is I'm going to take B, I'm going to attach it on to vector A. So you can see you can see I have vector A and then vector B. And so the end result is vector A plus B. So the A and the B is what I draw in order to get the final vector A plus B. So as you see A, so Rach, here's the answer to your question. A and B is like showing my work. The final answer is this A plus B. But how did I know to draw it from here to here? Well, after I drew A and then attached B onto it, that showed me where I would draw it to. So the next one, we have A minus B. So I'm going to take A and attach what onto it? Negative B. So I'm going to take A, I'm going to attach negative B. So that means that the end result is that vector right there. That vector represents A minus B because I have an A and a negative B. How would I do B minus A? Yep, take B and attach onto it negative A. And that shows me my end location, which would be B minus A. So do we sometimes, right? There's days I maybe look weird. Well, thank you. I appreciate that. That's like a year or two old. I can't remember. Well, thank you. That's why I wore it. Okay, so we like to express vectors in what we call component form. We use those markings where we have a horizontal component and a vertical component. Instead of parentheses, we kind of use these V's on the side. That's okay. Thank you for your input, Noah. YouTube Nation, we are definitely struggling in class today. I wore a shirt that reminds people of mint chocolate chip ice cream, and so we're talking about how much we love ice cream now. Okay, so what I'm going to do for this example is I'm going to show you how to come up with the horizontal component form, or I'm sorry, the component form of a vector. I'm going to take point P, which is the initial point, and I would take Q, which is the terminal point, and I'm going to draw the vector that represents those 2 points. So I go over 3 and I go up 4. And then vector Q, or I mean point Q, I go over 7, 3, 4, 5, 6, 7, and I go up 5. Is everybody okay with that vector? What I'm going to do is I'm going to turn it into component form. I'm going to write it so it has these kind of sideways, or these parentheses on the end that kind of look like these. And all I do is I determine how far have I gone horizontally with this vector. 4 units, yeah. 7 minus 3 gave me 4, correct? And how far have I gone vertically? 1. 5 minus 4 is 1. So if I were to plot 4, 1, you could see what I get. And I get basically the same vector, don't I? It's just shifted. And so when we determine the component form of a vector, what we are doing when we determine the component form of a vector, we're basically just shifting it so it's at 0, 0. Okay? And so you don't have to do that every time, but as you look at point P, point Q, initial point, terminal point, I want to just turn it into component form. So can somebody tell me what the horizontal component is? Nope. 7. What is the vertical component? -3. Yep, 4 minus -3 and -1 minus 2. You always start with Q because that's your terminal point. That's your ending spot. Everybody good with that? Okay, let's learn more about vectors. In order to do that, we need a little bit of space to write some notes. Turn to your very last page. You're going to have a few notes written on that very back page. It's that day where we had like 8 people in the classroom and I treated you kindly for one day as opposed to being insulting. Do you remember that? Never going to happen again. So what we're going to do is we're going to take a vector AB, and we're going to show you how to convert between different parts of a vector or different representations of a vector. If that's vector AB, that means I've gone up B units. That means I've gone over A units. We say that the length of the vector is the magnitude of V, or the absolute value of the vector. Can somebody tell me how I would get from A and B to the magnitude of V? Yeah, exactly. The magnitude of the vector is equal to the square root of A squared plus B squared. So you can see the trigonometry start to develop, right? There you have it. Magnitude of vector is square root of A squared plus B squared. As we said, vectors have both magnitude and direction. Can somebody come up with a trigonometric expression that involves theta? Tangent. Tangent of theta is equal to B over A. Good? Okay. Now, what that tells us is if you were given A and B, that tells you how to come up with the magnitude and the direction. Suppose it was the other way around. Suppose I had magnitude and direction. I wanted to come up with A and B. How would we do that? No big deal. Who can tell me a trigonometric function that has to do with those 3 values? Cosine. Cosine of theta is equal to A over the magnitude of V. So if you multiply both sides by the magnitude of V, you get magnitude of V times the cosine of theta is equal to A. Can somebody come up with a trigonometric expression that involves those 3? Sine of theta is equal to B divided by the magnitude of V. Multiply both sides by the magnitude of V, and you get magnitude of V times the sine of theta is equal to B. Those are all formulas that will be useful to us and important. Everybody see how we come up with them? We didn't make them up, did we? Okay, let's go back. We'll put them in our notes, and we'll try the examples. Magnitude of a vector. The absolute value of a vector, magnitude of vector, the length of the vector is the square root of A squared plus B squared. Do you remember the formula we used to come up with the direction? Tangent of theta is equal to B divided by A. You guys are shubishma. On the magnitude of each vector, we're going to find the direction as well. I have 5, -2. You don't have to draw this, but if I were to draw it 1, 2, 3, 4, 5, okay, and down 2, I were to draw that vector, it has a certain length and it has a certain direction. We would like to compute both. How do we find the magnitude? Square root of 25 plus 4. Get the root of 29. Thank you for sending the answers. I did. I wanted you to do that. It was something that was lacking in our class. We need math put to music. All right, so we got the root of 29. And now we're going to do tangent of theta is equal to b divided by a, or negative 2 over 5. I'm going to use up the negative. Which quadrant are we working in? Is everybody clear that we are currently in the fourth quadrant? Very good. I turn on my calculator, and I am going to tangent inverse 2 divided by 5, and it gives me 21.80 degrees. So, very good, 21.80 degrees. Subtracted from 360. So 360 minus my answer, and I get 338.2. So that's theta, and that's the magnitude of the vector. If you were to plot the vector, does it look like that matches with what our original drawing was? It sure does. Our last section, 7.6, when we're dealing with complex numbers, theta was always in radians. When you're doing vectors, because they're a real-world application, we will always be in degrees. I'll make that clear on the test and your study guide. Let's do this next one, and let's not do any of the arithmetic. Let's just think about plotting the point, okay? Vector 0, 3, 0, 3. Can somebody tell me what is the length of that vector? 3. Is that clear to everyone? Think about plotting it. Where does that place you? Straight up and down, and so that would be what? How many degrees? 90 degrees. See how we were able to do that without actually setting up any work? Isn't that nice? Yes, because we are smart. Scott's tots. I will give you all batteries for your laptops tomorrow. All right, magnitude of the vector. How about this one? Yep, 9 plus 16, I get square root of 25, which is 5. I said tangent of theta is equal to 4 over 3. So tangent of theta equals 4 over 3. Which quadrant? First, I tangent inverse 4 divided by 3, and I get the grand total of 53.13. We good? Okay. Last piece for us to finish off. Given A is 1, 3, and B is 2, negative 2, find the following. 3A. Super easy. We just multiply by 3. We got 3, 9. You can multiply a vector by a constant. You just multiply all the way through. You multiply both the horizontal component and the vertical component. Here we get 8, negative 8. For A plus 2B, we take vector A, which is 1, 3, and we add to that 4, negative 4. 1 plus 4 is 5, and 3 plus negative 4 is negative 1. Could you please compute 2A minus 5B on your own? Okay. What'd you get, folks? We all good? All right. then let's end with this. Okay, it says express the following vectors in component form. We're going to express them in terms of I and j. I'll show you what that means in a second. But basically, if you had the vector with a magnitude of 3 and an angle of 30, it might look something like that. Would everybody agree? Okay, so the question is, I'm given the magnitude and I'm given the angle. But suppose that instead of giving the magnitude and the angle, suppose I want it in component form, okay? Where I have A and I have B. Does anybody remember the formula we used to come up with A? Magnitude of the vector times cosine of theta. So we have 3 times the cosine of 30 degrees. Is there anybody out there who knows what the cosine of 30 degrees is? Root of 3 over 2. So 3 roots of 3 over 2. What is the formula then for B? The magnitude of the vector, 3 times the sine of theta. Anybody know what the sine of 30 degrees is? 1/2. So I get 3/2. So now, as you look, I have the following. I have 3 roots of 3 over 2 and 3/2. That is the actual coordinate for my terminal point for the vector in component form. Okay? Now, your book actually chooses to express this in another form, which we call IJ form. And it just looks like this. 3 roots of 3 over 2I plus 3 over 2J. I've never seen this come up in an engineering course. I don't see it being applied towards physics or anything else. I really don't think it's important that you know that. This is the, does everybody see how we get from one to the other? Yeah, this is the form that you will consistently use. Okay. Last example. Magnitude of 4, theta is 315 degrees. I want to come up with A. So I take 4 times what? Cosine of 315. Excellent. Positive root of 2 over 2. What is 4 times the root of 2 over 2? 2 roots of 2. What do I do to find B? 4 times the sine of 315 degrees, or 4 times negative root of 2 over 2, negative 2 roots of 2. So therefore, the component form of the vector is 2 roots of 2, negative 2 roots of 2. And if you wrote it in IJ form, it would be 2 roots of 2I minus 2 roots of 2J. Nope. Nope. We all good?